Good late afternoon, dear colleagues, dear friends. We are getting close to the end of the event. And the day before yesterday, we promised to you that it will be exciting and inspiring event. And I hope that you will agree with me that we kept the promise. At least it was certainly very, very interesting to me to listen to all these very exciting presentations that we had. And so we are delighted now to be able to present to you indeed rather quickly prepared summary of the talks, and hope that we can also discuss it later with you and elaborate on this more later. So this is just an intermediate result, more to come, hopefully. So we wanted to begin with this slide that we put together to remind ourselves where we come from. So we believe that systems analysis originated in operations research. And of course, for obvious reasons, it was mostly applied in earlier days, mostly applied to defense kind of questions, military questions. But this is where the systemic approach actually, where originally the systemic approach showed its value. And then, with the creation of EASA in particular, there's been expansion to systems analysis in more general sense. And later on, very importantly, it started to include policy analysis, and therefore the thematic focus also shifted to those questions where this advice from systems analysis was especially needed. And we heard a lot of presentations over the last 3 days on various applications, various very broad fields where it's currently being applied. Another stage that we wanted to highlight here has to do with interfacing with complexity science. So the global world is increasing in its complexity, in its interconnectedness, and therefore systems analysis also adopts a lot from complexity science. And now the most recent influence that we are all experiencing nowadays is that computational resources and also data availability is massively growing. And that creates new opportunities, but of course it also creates many challenges, many of which were discussed over the last 3 days. In this presentation, what we have done, we have come up with 10 overarching methodological dimensions. They are emerging from discussions that we are having at EASA constantly, on a daily basis. But also, they were very much inspired by the presentations that we heard over the last 3 days. One can call them even Hilbert questions. So they are very broad ones. So nobody, I guess, pretends to solve them, but at least we can approach those questions. We can think of them. We can try to elaborate on them. So what are those 10 dimensions? Heterogeneity, optimization, adaptation, uncertainty and emergence, resilience, bounded rationality, interconnectedness and integration, big data, and interfacing of science and society. So the list does not pretend to be complete. One can also add maybe other dimensions, but this is what we wanted to focus on in this presentation. So in the next slides, what we are going to do, we are going to, of course, we can only do it very briefly, but still give you an idea what are the main issues in each of these 10 dimensions, what we have learned from talks that we had during the conference, and also what are the current challenges and potential promising directions. With that, I pass the floor to Ulf.
Yeah, for each of these 10 dimensions, we have prepared a package for you, which starts out from setting the scene in the dimension and then goes very briefly through a couple of examples from the conference and concludes with an outlook on challenges and promising directions. And we must beg your indulgence that this necessarily is superficial as Elena has highlighted, neither is the list of 10 comprehensive, nor would all aspects within these dimensions be covered. The first dimension we have singled out is heterogeneity, and we hear this at the conference at so many occasions. We hear it at YASA. We have actually a cross-cutting project on heterogeneity, and it is certainly one of the trends in systems analysis in contemporary times. Heterogeneity is relevant for accounting for spatial structure. That goes without saying. Geographical structure means heterogeneity, but it also has many other dimensions of irreducible heterogeneity that are in the social domain, dealing with social diversity in terms of incomes, education, values, religion. Addressing heterogeneity often requires upscaling, which means clever aggregation, and we have heard about that, but also downscaling to project the results from global models to the regional and local level. In general, mean-based predictions turn out to be naive in the face of substantial heterogeneity, and variance corrections in the broadest sense are needed. This was very evident in Wolfgang Lutz's presentation, which emphasized that people obviously differ in very many dimensions, including age, sex, level of education, place of residence, and household structure, and that accounting for this heterogeneity enables us to achieve greater accuracy and therefore also a more meaningful projection capability over longer time horizons. Naive extrapolations can go wrong after 10 or 20 years, depending on the problems. With the right amount of heterogeneity built into the projection, the feasibility of longer projections becomes higher. Yami Moreno has reminded us that also in the online world there are many dimensions of heterogeneity. The average individual approach clearly does not work. As an example, he has shown us how users in online communities differ in terms of the amount of messages they originate and receive. So few individuals actually receive a lot of messages. I'm sure that feels different at the end of every email account you are sitting at, but most are mainly senders. This leads to a taxonomy of online users, and that is showing how to unfold in a clever way this heterogeneity. Raimo Hämäläinen has emphasized that heterogeneity also exists in terms of cognitive skills and cognitive biases, and he has shown us an example how the splitting bias is operating differently in groups of students and in stakeholder groups, with the former being able to overcome it with guidance and the latter unfortunately remaining stuck in the bias. Luciano Pietronero has then taken the heterogeneity discussion to a much higher level above the individual and applied it to new metrics he has devised for structuring economic complexity. And I think we were all impressed by this picture, which suddenly gave a lot of meaning to dynamics we have observed in an intuitive ad hoc way, and new patterns become evident and new forecasts conditional on these metrics become possible. So where do we see this going? On the spatial side, we are witnessing new methods being devised for spatial downscaling. We are witnessing model integration across GIS layers, and we are witnessing models that are not just single scale, but that address a complicated task of multi-scale modeling. On the social side, we are becoming increasingly aware that diversity matters, and we have new metrics for capturing salient aspects of heterogeneity and new models for involving and then also in turn closing the loop, predicting such metrics.
Let me proceed to the next topic, that is optimization. And maybe surprisingly, but we didn't hear much during the conference about various optimization methods themselves. Whereas this is, as such, although well established, but still a field where a lot of innovation is coming and will come. But it happened so that many speakers actually rather wanted to discuss why we want to optimize and for what, and who wants to optimize. So therefore, this discussion between descriptive, normative, and prescriptive analysis, what kind of analysis we need and when, took place. And follows from this, how do we choose objective functions to be optimized? So in this, I would like to remind ourselves about the talk by David Bell, who argued how simplified models and simplified preferences might be a way to go. In particular, they have been quite successful in economics and finance. So maybe the simple prescriptions is what decision makers prefer over a more complex analysis with different dimensions, different trade-offs, and so on. Obviously, as was mentioned already, each stakeholder has different preferences, but highlighting those and measuring those is not often explicitly done. So the example here demonstrates the work done at YASA in earlier days that actually is in a very simple and straightforward way demonstrates this heterogeneity in terms of preferences. He argues further that IASA should be at the forefront of knowing the preferences of interest groups and be as competent at representing values as it is at representing systems. We will come back to this in other topics as well. Another talk by Ali Abbas suggested, or reminded rather ourselves about decision trees approach, quite an established approach, but highlighted the importance of accounting explicitly for uncertainty when applying such approaches. The talk by Ralph Keeney continued that line of presentation and argued for value models, that is used as a synonym as objective function, and suggested several approaches how those can be constructed. So we always consider, so there are plenty of different ways how this could be done, and some structure that is imposed there certainly is a useful approach. So particularly preferential independence, utility independence, additive independence were mentioned as possible approaches. Here I'm also giving several other quotes from his talk. The effort required to build value models is very small relative to that to build traditional systems analysis models. Including policymakers in this explicit manner enhances their interest in the analysis since it addresses their decisions and their values. And then such analysis provide more insights for the decisions that may be made. In the talk by Ronald Yager, we saw how fuzzy sets could be used to tackle those things, those issues. So what the overarching question in his talk was, can we make use of preferences that are expressed in natural language, more preferred, less preferred, yes, no, and, or, and so on? How can we formalize this in models? And the suggestion was to use fuzzy sets and represent criteria as fuzzy sets over the set of decision alternatives. This approach enables then using logical operators such as and or to represent preferences. And then one can use different convolutions to derive the objective function to be optimized. So in optimization, therefore, what we see is that one possible direction is to emphasize prescriptive analysis. So to make more of prescriptive analysis and take more responsibility as scientists for those decisions that then policymakers will make. Another promising direction is indeed to collect much more empirical data on preferences of different stakeholders. So to create as much data, or maybe more data, on preferences as we do on some other parameters. Now this can be done through, for example, web-based tools quite easily. Natural language indeed is much more natural, of course, to collect this kind of data. So it's much easier to ask stakeholders in their natural language rather than to ask them to estimate some abstract variables. But it was also pointed by some speakers that optimization only makes sense when we have enough understanding about the underlying processes. If this is not the case, then we have to complement the formal modeling by various sorts of qualitative analysis, by scenarios that are derived based on modeling and that also enter models.
A cousin of optimization is adaptation. Adaptation is often more complex, but also more realistic than optimization. But ultimately, they need to coexist in systems analysis. Adaptation is appropriate when you deal with agent interaction. Optimization helps you to understand social planning from a central planner perspective. So adaptation is crucial for understanding human behavior and living systems. We now recognize that in adaptive systems, not only abundances are changing, but also strategies and traits are adapting. I very much like this idea that adaptive systems come to embody their history. They adapt to their environment, and in this way they come to embody their history. And we also need to overcome the naive idea that adaptation always helps systems. As we know from the tragedy of the commons, it can undermine a system's resilience and productivity. We saw that in the talk of Carl Sigmund, where agents adapt strategies for cooperation jointly with strategies for sanctioning. And we saw that as long as second-order sanctioning was permitted, cooperation could be stabilized despite the selfish interests of individuals. And in fact, through such adaptation, social institutions were emerging, could become established, here a form of pool punishment. Christoph Howard took that to the practical domain of experimental games, a public goods game, and the emphasis of this so-called climate game was on delayed gratification. One day, 7 weeks, or a whole generation, raising questions about intergenerational equity. And it turns out, and that confirms our intuition, that the longer the delay in the benefits, the harder it is to overcome selfish action. So on the social side, adaptation studies can help us to understand the emergence of social institutions for the governance of common good. And also, and I mentioned that in one of the discussions, understanding the origins, the evolutionary origins of cognitive biases. On the ecological side, which was not so much represented in the conference, such models of adaptation help us to understand functional biodiversity and also enable us to conduct evolutionary impact assessments for managing living resources.
Let me now go to uncertainty. That was part of many talks again, and point out that uncertainty and risks are not the same. One has to distinguish between these two notions. Usually we speak about parameter uncertainty, process uncertainty, and structural uncertainty. And one traditional approach to demonstrate the effect of uncertainty is, of course, sensitivity analysis of different sort. It's argued often that through learning, one can decrease uncertainty. But that, of course, may or may not be true. We may learn and realize that uncertainty becomes even larger, that options that were not even considered before now have to be considered. From practical perspective, what we want to do, we want to make decisions, and therefore decisions under uncertainty. And this is where the concept of robust decisions comes in. So robust decisions are those decisions that are good enough for all possible realizations of uncertainty. Deriving those decisions from technical perspective is a much more difficult task, usually, and therefore advanced mathematical methods have been developed for this. And those methods usually rely on various risk measures that are in one way or another included in models. And of course, this is nothing else but structural uncertainty that application of different measures may, of course, imply completely different solutions. So one has to be careful when choosing a particular risk measure. And in that sense, a very educating talk by Andrzej Ruszczynski gave us a very good and very extensive summary of possible approaches in that domain. Probabilistic approaches to make decisions under uncertainty and risks that range from utility models where risk measures are included in utility functions to another approach that prescribes including risks into constraints, so so-called chance constraints. And also those constraints can actually use the entire distribution, not only particular moments of those distributions. Different risk measures that can be used such were mentioned as mean semi-deviation, average value at risk, and especially recently are becoming popular various metrics that are based on entropy. There are many issues here. We highlighted two. So if the dynamics is considered, one has to take care about time consistency when these risk measures are applied. But also, more importantly, availability of big data and now new techniques of artificial intelligence and so on. So if those could be merged with this stochastic optimization methods, that might be a very promising avenue to go in this domain. The talk by Werner Römisch gave examples, basically, of application of stochastic optimization to management of energy system, where Monte Carlo samples from empirically derived distributions of uncertainty were used in optimization problem. Excuse me. This time of the year is difficult to avoid catching cold. So, where did we stop? Monte Carlo, yes, Monte Carlo samples were used to derive, derived from distributions in order to then estimate the risk measures. And then optimization tried to maximize at the same time expected revenue and minimize the risks. And used average value at risk as a risk measure. And important here to mention in the example that in a German gas transportation network that was analyzed, this inclusion of risk aversion only costs like 1% of the expected revenue. So this is a relatively cheap measure that, however, enables these robust solutions that we mentioned before. Can you continue? I have to drink water.
Yeah, Marc Beaumont then showed us a novel technique for so-called approximate Bayesian computation, and that helps us with dealing with models with very large numbers of parameters that could previously not be tackled with likelihood methods. But through the approximation he described, it becomes possible to derive posterior probabilities for these parameters. So you're not only getting a parameter estimate, you're getting a whole distribution of likelihoods of parameter values, and that means you have also the uncertainty in your parameter estimation quantified. Robert Lampert talked about new decision science for complex systems, and in particular was emphasizing the importance of scenarios. The idea he put forward was that policy-relevant scenarios are emerging from the analysis. They are not the starting point, but a product of these analyses. David McCollum then applied these ideas to harnessing, applied systems analytical tools to develop sustainable energy scenarios for the 21st century. And in particular, he integrated uncertainties for climate change mitigation, ranging from technological uncertainties over social uncertainties and including also political uncertainties. So the challenges in the modern study of uncertainty are to deal with multi-stage stochastic optimization, to identify robust solutions with respect to input uncertainty, to deal with modern kinds of sensitivity analysis with respect to model assumptions, and in particular with respect to risk measures. And clearly the complexities are increasing, so the technical demands on the modeler, but also on the computational resources are growing. Our next package is on emergence. Emergence is one of the reasons why dealing with complex systems is so hard. Through emergence, macroscopic features arise from microscopic processes. Examples are crowd patterns, incipient social ordering, meme trends. In all these cases, you have phenomena of emergence. That's why they are often associated with surprises, with tipping points and regime shifts, and are fundamental to capturing the complexity formation in system models. There are two main sources of emergence: self-organization and adaptation. This, therefore, transcends a simple reductionism, as new levels of systems organization can emerge endogenously in a systems model. And that is important for understanding network dynamics, contagion, collapse, resilience, and systemic risk. We saw examples of this emergence in Brian Fass' talk on spatial pattern formation as an example of a typical emergent phenomenon. Here you see his pictures of centers that arise as spatial zones of coherence, which recursively depend on other centers. And he brought up an interesting connection with philosophical developments on autopoiesis and structural coupling that are making sense of such self-referential entities. Simon Levin applied this kind of thinking to cascading failures across networks of interacting agents, and here the emergent property in the system is a systemic risk. At the macro level, you have systemic risk originating from the micro level interactions, and this kind of thinking makes it then easier, and he exploited that in his News and Views article, to see universalities across applied domains, because this phenomenon of emergence then has a certain universality. In the future, we will presumably see some methods for the automatic identification of order parameters, a long-term concept in physics, for measuring emergent properties. Currently, these are conceived by the modeler, by the theorist, but we probably will see machine learning algorithms for extraction of order parameters that can contribute to early warning systems, and we will also, I think, see an increasing level of integration between the two sources of emergence, self-organization on the one hand and adaptation on the other hand, which in many models are still treated separately.
Resilience, that wasn't very successful in my case, I'm sorry for this, but has the following aspects. So first of all, there is no one definition of resilience. It's context dependent, different definitions have been suggested, but also measuring. So how do we measure resilience? That's again, at the moment is different in different domains, and even within each domain there are different ideas how to do this. However, what's common is that resilience is usually considered with respect to two types of disturbances or perturbations: shock perturbations and stress perturbations, depending how they act, whether they act at one moment of time or they act continuously. And so there are four dimensions when we want to improve our resilience. We want to anticipate, we want to mitigate risks, we want to adapt, and also repair. So with this major directions, we had a number of talks related to this topic. One talk by Stefan Turner on new types of risks that are emerging now from interconnectedness between different elements, systemic risk. And he gave us an example of financial systemic risk, which is, of course, one of the main risks at the moment that are caused by this interconnectedness. Even there, definition of systemic risk is argued. In his presentation, he suggested that systemic risk is a situation when system stops functioning due to local defaults and subsequent cascading, reaching out large part of the system. Systemic risk usually originates in two phenomena. One is synchronization of micro-level behavior. So all people suddenly go to bank and claim their money. And also from the existence of networks. So banks are connected via interbank network and via lending and borrowing, and that also gives rise to systemic risk. He pointed that banks usually have no means to manage systemic risk, even to anticipate it, and therefore this is a regulator's role to do so. But interestingly, in this study, they suggested how to transfer this role back to banks by imposing particular fiscal measures, in this case, so-called systemic risk tax. Martin Scheffer gave us a very interesting talk. I'm sure you all remember the following table here on the stage that very clearly illustrates what a critical transition is. A very natural desire of the society is to anticipate such events, and therefore to create early warning signals. So from theory, it has been suggested this slowing down effect may be very instrumental in providing these early warning signals, and it has been shown in numerous studies that he reviewed in his talk that both in models, in empirical data, and also in lab experiments, we do see that this kind of theoretical-based early warning signals indeed anticipate these critical transitions. In the talk by Xu-An Chong, there was a number of examples were given to illustrate how this method was applied, particularly to economic and financial data. Here, in the other talk by Petr Šepalin, other types of risks were considered, risks from natural hazards, namely from earthquakes. And yet another important problem was highlighted, that completely different approaches are used at the same time, simultaneously, to offer these early warning signals. So how to make use of alternative approaches. So what he suggested is to combine different methods, and he also demonstrated how this combination actually increases the predictive power of such methods. So what we see here in this very developing field at the moment is that early warning signals are very much needed by policy, by society. They can be either theory-based, as it was demonstrated, for example, based on the slowing down effect, but they can also actually derive this warning signals directly from data. So this has not been discussed a lot during the conference. However, these two approaches are out there. The difference between forecasting and predicting, one has to realize, and combining different methods may be instrumental for both of these. So increasing interconnectedness, as we just said, indeed creates new types of risks, and new methods, new models are needed to study systemic risk, both to measure, to model, and then to manage.
One key trend that systems analysis will need to address is a growing skepticism towards a rational actor model. Bounded rationality is widely recognized through cognitive biases and limitations, and there's just no way that we can keep this mess out of systems analytical models. It's actually a polite phrase. Bounded rationality suggests that it's mostly rational. Often one gets the impression it's mostly irrational, and that comes from the importance of heuristic thinking, which were developed in one kind of context and applied to another context. Su-Hong Cho showed us that this bounded rationality and a particular cognitive bias called familiarity biases is prevalent in investment decisions, so quite important also then for economic dynamics. And what I found very surprising is that he detected a genetic basis for this familiarity bias. So in particular, he found that alleles or genetic code fragments that are rare in a population cumulatively help with lessening that bias. Very fascinating. Robin Keller showed us that bounded rationality can arise from myopic decision making. This can be revealed by eliciting what she described as objectives hierarchies. And one particularly stunning example were the fishermen from the tuna fishing fleet of San Diego who were facing new customer preferences and consistently made the wrong choices, as we see in this table, leading to their commercial extinction. Xijing Tang took the study of bound rationality to the collective level, where it may be involved in spontaneous social dynamics and collective actions, sometimes of undesirable sort. Combined with machine learning, the monitoring of word frequencies in online communication can facilitate anticipation, but we also heard about how difficult that is to put into practice. Sergio Rinaldi was then talking about a domain of human behavior that is often seen as the most irrational, and yet he found that the love dynamics in relationships are amenable to systematic analysis and rough predictions based on simple models. But one prerequisite for doing so was again accounting for the heterogeneity of personality types. There's an emerging taxonomy of cognitive biases and limitations, and that should help us with the task of integrating these into models. Ultimately, we need more realistic descriptions of human behavior and putting these into scenarios and forecasts.
In the topic interconnectedness and integration, the main aspects that we singled out here is interface between conceptual and mathematical models, the necessity to add this qualitative kind of models into formal considerations. Another type of interconnectedness, some of which was already mentioned before, but more explicitly here between regions and sectors, linking regional and sectorial models. It was also argued that perhaps explicit inclusion of people and also institutions into models is a useful approach. And finally, another aspect of integration is that currently alternative models exist to describe the same phenomenon that originated in hydrology and climate change, but now also happens in other fields. So here, the talk by Louis Betancourt on cities as systems gave a very good example of how cities are important example of interconnected systems. And these are networked systems where people are connected, infrastructures are connected, sectors are connected, and so on. So, and therefore, if we want to understand cities and if we want to govern them systems, then of course we have to integrate all those sectors that are depicted here on the slide. And in particular, explicit integration of people in the economy, even to the extent that the so-called production function is suggested, where people are basically part of that. That's quite a novel approach to integrate people and economics. In the talk of Nebojša Nakicenovic, the practical aspect of it was brought up. We all heard about it several times during the conference. That the UN has adopted 17 sustainability development goals that range from poverty to hunger, health, education, water, cities, and so on and so forth. So 17 is already a big number. So how to understand connections between those? Maybe for some of them there are synergies. For some of them there will be trade-offs. So how we want to work in this 17-dimensional space? Particularly urban metabolism. So again, we come back to the idea that city is an interconnected system. So maybe we should learn from biology and try to apply those approaches that have been suggested there to now analyze cities through this concept of metabolism. On the practical side, IASA has been developing methods to come up with integrated policies. So with policies that try to achieve several goals at the same time. And then the example that Naki demonstrated, and then David McCollum also, it was clearly shown how aiming at several goals can actually help come up with less costly solutions than aiming at one goal only. In a talk of Beth Fulton, she emphasized the aspect of different scales. So we have to handle multiple scales, And from experience, she reported to us that it's actually weakest at the intermediate scale. So we have less knowledge at the intermediate scale, and also in those aspects that have to do with social dimension. Decision makers often trust only on their own mental models, and sometimes, or maybe often, use even inconsistent models at the same time. Therefore, one has to much better understand those cognitive biases, as was mentioned earlier, and also build trust and study attitudes, involve psychologists to come up with much more realistic picture. Another example of interconnectedness, and where interconnectedness plays a crucial role, is the water issue. So the water is truly interdisciplinary area, as it was shown to us in the talk by Yoshivada. And here, to suggest solutions to solve scarcity problems really requires linking across different regions and sectors, and also include people's attitudes. In this domain, what we have seen as promising directions are so-called multi-layer networks, or multiplexes, when different connections between the same agents, the same nodes, are considered at the same time. So-called nexus models that link different sectors together is also another promising directions at the moment. For those models that represent the same phenomenon, multimodal ensembles, or integration across those multimodal ensembles, is yet another promising methodology. Another one is working across scales, geographical scales, also disciplinary scales, and of course was mentioned many times already and will be mentioned later in the talk, participatory involvement of stakeholders at all stages of the analysis.
Another big trend that must not go unmentioned is big data, even though the allure of it might already be tapering off a little bit. But there is clearly this explosion of data availability through census, through free information policies, increasing accessibility, and through crowdsourcing. And that just creates a lot of exciting and promising opportunities, enabling better model calibration and database decision making. Boris Mürken showed us how classical techniques for clustering, ranking, aggregation, tree construction, and visualization can be refined and extended, and all of these methods are important for dealing with big data. Alexei Gvishiani showed us how sensor networks in particular can provide unprecedented volumes of location-specific and real-time data, and as one example mentioned there are over 100 observatories that are linked together in the global intermagnet network monitoring the Earth's magnetic field. Dirk Helbing then also capitalized, apart from his very interesting work on cooperation evolution, on this new swath of global data becoming available and enabling novel models and predictions. And two dimensions he has worked on is using such models for predicting conflict probabilities in a regional setting and for predicting epidemic spread in a global setting. Such predictions can thus give better resolutions in space and time than was previously possible. Mauro Martino then finally showed us exemplified how our visual system is very well suited for processing data of high complexity and bandwidth if suitably presented, and I think we saw that he had very neat techniques for achieving this suitability. Such scientific visualizations not only help with comprehending what's going on the part of the scientists, but also play a key role in enticing interest and promoting understanding among wider audiences and the lay society. As I said, big data is already a word that is not everybody's darling anymore. It democratizes access to scientific information. It stimulates fundamentally innovative investigations and algorithms. It promises improved understanding and forecasts, enables comprehensive and compelling visualizations, but there's a downside, and here I've just listed a few of those. The data we have access to is often only weakly structured, has low quality and meager representativeness. It needs to be filtered using massive computational resources, making that a daunting undertaking in some domains. It raises fundamental privacy concerns, And at a very fundamental philosophical, epistemological level, it creates a deluge of false positives that could undermine our currently prevailing understanding of significance.
Big data entering the 10th topic in our list very much. This is interfacing of science and society. And this is the topic that was at least explicitly or implicitly touched upon by every talk in this conference. And this is not by coincidence. This is because, indeed, the systems analysis now entering this time when society must form partnerships with science and work in true partnership to come up with realistic, feasible solutions. However, there are plenty of challenges and choices to be made. So how to involve stakeholders in research? What should be their motivation? What should be motivation of scientists to do so? What should be motivation of stakeholders to participate in this? Mutual understanding is still to be developed. So both sides talk very different languages. So finding a common language is a task to be tackled. There is also equity issue. So different groups of stakeholders, how should they be represented? So what is the fair way of representing various, sometimes controversial interests of stakeholders? Another issue is that there are different types of objectives. Some objectives are easy to reveal, some are less easy to reveal. And revealing the true objectives that guide our decisions is yet another challenge here. There are two types of acceptance problems that we are facing here. Not only more common problem that we are always discussing is that scientific results not often are accepted and not often are followed by policymakers, but there is also another problem of acceptance on the other side. Not often scientists, or not always scientists, want to accept the real information about stakeholders, their real preferences, their real objectives. They tend to ignore those and create models sometimes of idealistic stakeholders that may not be existent in reality. As I said, really each talk in one way or another touched upon this issue. So here we highlight just a few. The one by Robert Dijkgraaf, who talked about science and policy interface and the bridge that is obviously needed. So hopefully the bridge that will be a little bit better than the one on the picture. International field is where this is happening, that also creates yet another complexities related to cultural differences and so on and so forth. Quality control is also very important, and the efficiency of the entire process. Ulf Yager also highlighted similar issues. It often happens that we rather have qualitative results rather than quantitative. And therefore narratives are sometimes more efficient ways of building this communication rather than numbers. In the mini panel by Marcus Ammann and Martha Williams, they discussed what can help this acceptance problem that I mentioned before. So Marcus gave us the recipe of 4 essential ingredients that at least are necessary conditions for this acceptance. It's credibility, salience, transparency, legitimacy. It was highlighted by Martin Williams that uncertainty is a very important issue in this communication, and how the uncertainty should be communicated and can be communicated to decision makers. It was noted that, of course, Monte Carlo analysis, that is very established approach, is still helpful, but also this recent techniques such as emulators, for example, that can provide computationally efficient way of representing and tackling the uncertainty. In the other mini panel by Paul Chatterton and Lenta Z. So they presented crowdsourcing as an approach to build this partnership between science and society. So through web-based tools, one can collect a lot of data and establish interaction with various stakeholders depending on the task of the project. They also shared with us some lessons on crowdsourcing that they have been doing here at YASA. At another geographical scale, Anna Skolopik presented to us lessons that they learned from their stakeholder exercises that they run in a small community in Italy. Here, what we wanted to highlight is that reducing complexity may be an important necessary step towards an efficient analysis. So they gave an example how from 25 stakeholder groups that they originally had, through the use of cultural theory that has been developed here at YASA, they were able to reduce that dimensions to 3 relatively clear types of different stakeholders and then analyze it already at that level. So this is a very developing field at the moment. Of course, here we only list some aspects that we think are promising. It's been mentioned many times that involving stakeholders in the entire cycle of analysis, from the very beginning, from the posing of a problem, all the way to deriving conclusions, deriving recommendations is what's highly recommendable, if this is possible. So enabling this, taking care of this, that's an important effort that scientists have to make. It was pointed that one has to distinguish between modeling of decision makers and modeling with decision makers. Both approaches may be useful depending on the goal. The new generation of decision makers, do we want to offer them education in systems analysis? Do we want them to understand us more, understand more our language? So that may also be a way to go. Of course, there are also ethical dimensions in this. One of them is trust. So how to build the trust? How to build the trust that would then again help this acceptance problem? Maybe other disciplines should be involved. Maybe we should explicitly involve psychologists that would help us building those partnerships through trust. And then there is always a technical side of it. And now with the new technologies that we are possessing, the feeling is that much more can be done, for instance, through these web-based tools that are being developed.
Before we now finally turn the floor back to the panel discussion that is wrapping up this closing session, we wanted to reconnect to a few of the big questions. So systems analysis has grown up. The demands for systems thinking and systems analysis are clearly on the rise. At the same time, and synergistically reinforcing that trend, the capabilities of systems analysis are rapidly growing in terms of data, models, methods, and computation. Yet, humility and caution remain essential. Overselling must be avoided, and challenges remain formidable. Systems analysis has developed a colorful diversity of approaches, and we have heard the question, is it a field? Is it sufficiently united, or are we just using a term here? And I think one answer to that question is that the mobility of methods traveling to new applications along the conceptual network of systems analysis is vital for the field's cohesion and vibrancy. And in this regard, our conference has hopefully made a contribution. Thank you.